Hello all, welcome to the first lecture of number theory. The prescribed textbook for number theory is the Elementary Number Theory with Applications written by Thomas Cauchy. The first module has the first section. Starting section of the first module is section 1.3, that is mathematical induction. So before directly starting the section, we have to look at some prerequisites which are given in the sections 1.1 and 1.2 of this chapter, that are order relations, summation and product notations. As you know all these things, we can just go through these ones very fastly. As you know, the number theory means it is the theory of numbers, that means mainly by integers. It is concerned solely with integers. So we can start with going through the number systems. Okay, we know the set of integers is denoted by the letter Z. So Z denote the set of integers. The set Z denotes the set of integers that we already know. That means Z, the set Z is equal to set of all negative integers, minus 3, etc., minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. Okay. And we denote for an element, we can say that an element x is in Z by this notation is belong to. So this notation means for belongs to. So x does not belong to Z, we can write simply as like this. Okay, in any set we can use this one. Okay. There are positive integers 1, 2, 3, etc., which are also called the natural numbers or counting numbers. So these are the natural numbers or counting numbers that you already know. So the set of natural numbers are denoted by the letter etc. is denoted by the letter n, or these are the positive integers. So we are denoting this by Z plus. So Z plus and the set of natural numbers is all are same, the same set, or counting numbers. These are also called the counting numbers. And with these natural numbers, if we include 0, then the system of numbers is called the whole number system, and this is denoted by W. So there are natural numbers, and natural numbers are contained in whole numbers, we know, and whole numbers are also contained in the set of integers. And finally there are other numbers which includes numbers, irrational numbers, like after that there are rational numbers. We are denoting the rational numbers by Q, and we know the set of all numbers of the form A by B, where A and B are integers. So the numbers formed in this way is called the set of all rationals or rational numbers. And generally it is denoted by the letter Q. So Z is contained in Q, and there are some other numbers which cannot be written in this form A by B, like E, the natural number E, Euler number E, and you know this is an irrational number, and another number pi. These are all irrational numbers, and there are some others like this. These type of numbers are called irrationals, and mainly we are denoting this irrational numbers by the letter capital I. Okay, so these two are different sets, disjoint sets. Q and I are, they have no common element, but if all these numbers are included, we form the set of all real numbers, or meaning any number which can be represented in a line is called the real number, set of real numbers, or which represents the real number system. And we know irrational, rational, all numbers we can mark in a real line. So the numbers which can be represented in a line is called real numbers. Okay, so this about the a quick view of the number systems. Now we have to move to the one relation that is called order relation. Order relation. So if we take any two integers, let a and b be any two integers. We know a and b any two integers. For example, if we consider 2 and 3, we can compare these two, isn't it? We can say that 2 is smaller than 3 or 3 is greater than 2. So if we take any two integers like this, for example, -1 and 0, we know -1 is less than 0. So there is less than relation. Or if we take 3 and -4, we know 3 is greater than 4, and if we take 3 and 3, we can say that there is equalities there in between these same numbers. Okay, so there are between any two integers, or if we are given any two integers, we can compare them, or there is a relation connecting them, either it may be less than, or it may be greater than, or it may be equal to. Okay, so for any two integers a and b, either a is less than b, or a equal to b, or a is strictly greater than b. So if a is not less than b means a not less than b, and if a is not greater than b, that we can denote it by like this. So between any two integers we can say this rule. Okay, a less than b, or a equal to b, or a greater than b, and this law is known as, so there are between any two integers, this is the only possibilities. These are the three possibilities. So this is known as the law of trichotomy. This is known as, it's a very important, law of trichotomy. That means any two, in between any two integers, the relation is either a less than b, a equal to b, or a greater than b. Now next we have to look at the section 1.2, that is summation and product notations. Summation and product notations, these are just the notations used for adding the sums or sum of some numbers. For example, the sum such as, suppose there are numbers ak plus 1, etc. am, and we have to add this. Let us denote the sum ak plus 1 plus etc. plus am. Then we know we can write this as summation. We can take another variable, let it be I. I varies from 1 to, from where it starts from k and ends in up to m. So summation I varies from k to m ai. Like this we can write. And this I varies from k to, or we can write I equal to m up to I equal to m ai. This means ak plus 1 etc. plus am. Okay, this variable I we used for notating this is known as the dummy variable. So I is the summation index, and it is also called the dummy variable. So for example, if we consider summation I varies from -1 to 2, I into I minus 1. What will be the sum of these terms? This will be equal to, as we know, this will be equal to, first of all we have to give the value -1. So I equal to -1 means -1 into -1 minus 1, plus then I gives to value 0. So 0 into this one means 0 into 0 minus 1. Then 1. 1 means 1 into 1 minus 1 plus we have to give the value to 2 into 2 minus 1. Okay. So minus 1 into minus of minus 1 is minus 2. Minus 1 into minus 2, that is 2, plus this one will be 0. 1 minus 1 is there, again 0. Then 2 into 2 minus 1 is 1. So 2 into 1 will come. So this answer is 4. Okay, so this is the notation and the summation. Okay. Again another example. We can look at one more example, that is summation j varies from minus 1 to 2, 5j cube minus 5j the whole cube minus 2j. Okay. So this is actually the difference of two indices are there. Then take the summation, or if this can also be done in this way, that is summation j varies from minus 1 to 2, 5j whole cube minus summation we can give into brackets. So summation minus of summation I varies from minus 1 to 2, 2j. Okay, or in this 2j, or we can open the bracket, 5 cube is, we know it is 125j cube minus we can take this constant because the summation only for j. So 2 is a constant, so we can take the outside. J varies from minus 1 to 2. Okay, so this is equal to, again 125 we can take outside. Summation j varies from minus 1 to 2, j cube minus 2 into summation j varies from minus 1 to 2 j. Okay, so 125 into j cube minus 1 the whole cube plus 0 cube plus 1 cube plus 2 cube minus 2 into minus 1 plus 0 plus 1 plus 2. Okay, again this must be equal to 125 minus 1 plus 1 will be 0. So minus 1 plus 1 plus 8 minus 2 into minus 1 plus 1 will get cancelled. 2 into 2 will be there. So 125 into 8 minus 4. So the answer is 996. Okay, you can verify the answer. So like this we can do all the summations. Now one more example. Evaluate summation d where the conditions for d is greater than or equal to 1 and d divides 6. This notation is for divides, where d divides 6 means d is a factor of or divisor of 6. So we have to find this summation. So first of all we have to consider the values, which are the possible values for d. D must be greater than or equal to 1. So we have to consider the factors of 6. Factors of 6 are 1, 2, 3 and 6 itself. Okay. So the summation means summation d greater than or equal to 1, d divides 6. D means sum of, we have to consider d, since d is greater than or equal to 1, we have to consider only the positive divisors. So actually this notation means the sum of positive divisors of 6 or positive factors of 6, that are 1 plus 2 plus 3 plus 6, which is equal to 12. So the answer is 12. Okay, so this about the summation notation, and also we know the product notation. Next is product notation. Product notation is, we know the product of 1 into 2 into 3 into etc. into n. We can write it as product n. N varies from 1 to, some k varies from 1 to n k. We can write like this, or this is actually n factorial. So n factorial, we know it is f of n. So we can write it as n factorial. We can write it as product k varies from 1 to n k, like this. Now we can check one problem. Evaluate product I equal to 2 to 5, I square minus 3. Okay, so this is equal to I equal to 2. First of all, we have to give to 2 square minus 3 into 3 square minus 3, then 4 square minus 3, and 5 square minus 3. Okay, so 2 square is 4 minus 3, that is 1. 9 minus 3, that is 6. 4 square 16 minus 3, that is 13. 5 square 25 minus 3, that is 22. Okay, so the answer, by multiplying all this, we will get 1716. So next we move to our section, the first section of this first section in the syllabus of number theory, that is section 1.3, mathematical induction. So as number theory deals with the theory of numbers, mainly integers, we know in order to prove the results in number theory, some tools are required for proving the theorems and results. So one of such a tool is mathematical induction. So in order to prove the results, we are using mathematical induction as a tool. One of the famous results in number theories, we know the basic results for positive integers. We know the sum of first n positive integers is given by, that is summation I varies from 1 to ni, is obtained as n into n plus 1 by 2. We know this result is true for every positive integers. Okay, but how to prove this result? And also another famous result, summation I varies from 0 to n minus 1 r raised to I is r raised to n minus 1 by r minus 1, provided r not equal to 1. But we don't know how to prove this. So in order to prove these type of results which are valid for every n positive integers n, we are using some tools, and principle of mathematical induction is one of such tool. So before we move to this mathematical induction, we need to know one famous property, and an important famous and also an important property of integers, mainly of positive integers, that the property is known as well ordering principle. The well ordering principle. This is an important result for positive integers. So the well ordering principle, the statement is that every non-empty set of positive integers has a least element. Every non-empty, that means the set which contain at least one element. Every non-empty set of which type of numbers? Set of positive integers. Every non-empty set of positive integers has a least element, has a least member. The smallest value will be there in every non-empty set of positive integers. For example, if we consider the set 17, 23, 5, 18, 13. We know this set contains only positive integers, and it is a non-empty set, and we can identify that 2 is the this set has 23. This set has a least element which is 5. The elements that means the elements also can be ordered in this form. in the ascending order as 5, 13, 17, 18 and 23. Like this. So by virtue of the well ordering principle, the set of positive integers is said to be well ordered. So if there is a well ordering principle in that set, the set is said to be well ordered. So well ordering principle means that this is a basic tool for proving any result in number theory. So this mainly we have discussed only two tools, that is, one is the well ordering principle and another is principle of mathematical induction. We have just mentioned only the principle of mathematical induction. In later videos we will discuss in detail. Okay, so we have discussed another tool, that is the well ordering principle. So well ordering principle states that the statement is every non-empty set of positive integers has a least element. Every non-empty set of positive integers has a least element. Now we can check one application or one example of this result. We can consider one situation. Prove that there is no positive integer. Prove that there is no positive integer between 0 and 1. Prove that there is no positive integer between 0 and 1. So we know in number theory or in any proof, we can also try the method of contrapositive. Okay, here we need to prove that there is no integer in between, no positive integer in between 0 and 1. So we suppose on the contrary or contrapositive, such that there is a number positive integer between 0 and 1. So proof is by contrapositive. So suppose that there is an integer, there is a positive integer between 0 and 1. Let it be A. അതിനെ നമ്മൾ A എന്ന് വിളിച്ചു. ഓക്കെ, അപ്പോൾ ഒരു പോസിറ്റീവ് ഇൻറ്റിജർ എങ്കിലും ഉണ്ടെന്ന് എടുത്തു. Now we consider another set. Let the set S is equal to set of all n numbers positive integers n belong to Z plus, that is set of all positive integers such that 0 less than n less than 1. Okay, അപ്പോൾ 0-ൻ്റെയും 1-ൻ്റെയും ഇടയിൽ വരുന്ന എല്ലാ പോസിറ്റീവ് ഇൻറ്റിജേഴ്സിൻ്റെയും കളക്ഷനെ നമ്മൾ എസ് എന്ന് വിളിച്ചു. We need to prove that there is no such a positive integer. So we assumed on the contrary that there exists at least one positive integer A in between 0 and 1. And we have considered the set of all positive integers in between 0 and 1. So clearly this S is non-empty, isn't it? So S is non-empty. That means S contains an element. Why? S is non-empty since, what is the reason? We have assumed that there is a positive integer A in between this, since 0 less than A less than 1. So A belong to, implies A belong to S. So since A belong to S, S is non-empty. So since 0 less than A less than 1, A belong to S, so S is non-empty. So S is a non-empty set of positive integers. That means that is S is a non-empty set of positive integers. S ഇപ്പം എന്തായി? non-empty set of positive integers ആയി. So by definition or by the well ordering principle, now we can apply the well ordering principle. What was the well ordering principle? Every non-empty set of positive integers has a least element. Now we have proved that we have obtained that S is a non-empty set of positive integers. Therefore, by well ordering principle, I'm simply writing WOP. Don't write like this. This is just for easiness. So by well ordering principle, S has a least element. S has a least element. Let it be L. So there is a least element L where 0 less than L less than 1. Okay. So S has a least element. That means L is a positive integer between L is a smallest positive integer between 0 and 1. So since L is greater than 0, L is positive, this implies L square is also positive, and we know in between any two numbers, between two numbers 0 and 1, we know 1 by 2. This just for, suppose we know 0 is less than 1 by 2 is less than 1, and what about its squares? 1 by 2 whole square will be less than 1 by 2, isn't it? So if there is a number in between 0 and 1, its square will again be, but in for all numbers, for any number which is any rational or any number which is greater than 1, we have a square must be greater than a. But if the number is in between 0 and 1, then its square will be less than that number. Okay, so keep in mind these things. Now we have obtained by well ordering principle that S contains a least positive integer L between 0 and 1. So what about L square? Since L is in between 0 and 1, L square must be in between 0 and 1, and it will be less than L also. So L is less than 1 and this is greater than 0, since L is greater than 0. Okay, so L is 0 less than L square less than L less than 1. So then we have 0 less than L square less than L, which is less than 1. So L square also belong to S. L square also belong to S. But L square അപ്പോൾ ഇവിടെ ഉണ്ടെന്ന് കിട്ടി, S ഉണ്ടെന്ന് കിട്ടി. പക്ഷേ L square എന്താണ്, L-നേക്കാളും ചെറുതാണ്. But L is the least element. So this contradicts the assumption that L is the least element. Okay. L ഒരു ലീസ്റ്റ് എലമെൻ്റ് ആണെന്ന് പറഞ്ഞതിന് ഇത് കോൺട്രഡിക്റ്റ് ചെയ്തു. കാരണം എന്താണ്, എൽ സ്ക്വയർ എല്ലിനേക്കാളും ചെറുതാണ്. ആൻഡ് വി ഹാവ് ഒബ്റ്റെയിൻഡ് ദാറ്റ് എൽ സ്ക്വയർ ബിലോങ് ടു എസ്. എൽ സ്ക്വയർ എല്ലിലുണ്ടെന്ന് കിട്ടി, എസ്സിലുണ്ടെന്ന് കിട്ടി. എസ്സിലെ ലീസ്റ്റ് എലമെൻ്റ് ആണ് സ്മോൾ എൽ എന്നാണ് നമ്മൾ അസ്യൂം ചെയ്തത്. പക്ഷേ എല്ലിനേക്കാളും ചെറിയൊരു നമ്പർ എൽ സ്ക്വയർ ബിലോങ് ടു എസ് എന്ന് നമ്മൾ പ്രൂവ് ചെയ്തു. ദിസ് മീൻസ് ദാറ്റ് our assumption was wrong. That means there is no positive integer between 0 and 1. So this contradiction proves that there is no positive integer between 0 and 1. Okay. So in the same way you can prove another problem, that is prove that every non-empty set of non-negative integers has a least element. Every non-empty set of non-negative integers has a least element. Non-negative means this set containing 0 also. Okay, so it may contain 0 or may not contain 0. So you can, the hint for this is do it as two cases, one containing 0 and another not containing 0, like that. Okay, so in the same way we can prove that this result will also be true. Okay, let's stop here. Thank you all.